Welcome to your AP Statistics Chapter 21 um, lesson, where we're going to discuss more about hypothesis test and intervals, both our methods of inference. This is Mrs. Brown, and I'm here with Daisy and Scout, and we are ready to talk statistics. All right. Remember, to perform a hypothesis test, the null must be a statement about the value of a parameter for a model. We're going to use that value to compute the probability that the observed sample statistic, or something even further from the null value, might occur. So how do we choose the null hypothesis? The appropriate null arises directly from the context of the problem. It is not dictated by the data, but instead by the situation. There is a temptation to state your claim as the null hypothesis. However, we can't prove a null hypothesis true, so it makes more sense to make our claim the alternative hypothesis. That way, when we reject the null, we are left with what you wanted to show. All right, sometimes people struggle a little bit with interpreting a p-value. The main thing to remember it is a conditional probability, and the condition is that the null hypothesis is true. It is the probability of obtaining the observed statistic, or one even further from the null value, given that the null hypothesis is true. When we see a small p-value, we could continue to believe the null hypothesis and conclude that we just witnessed a rare event, but instead we trust the data and use it as evidence to reject the null hypothesis. However, big p-values just mean what we observed isn't surprising. That is, the results are now in line with our initial assumption that was in the null hypothesis, so we have no reason to reject it. When we see a large p-value, all we can say is that we don't reject the null hypothesis. So sometimes people, want there to be a value that we check the p-value against, because just this concept of a low p-value seems kind of slippery. So sometimes there is a level of evidence that's established ahead of time, and we call that an alpha level, which is represented by a Greek letter alpha. If our p-value falls below alpha, we reject the null and our results are statistically significant. Common alpha levels are 0.1, 0.05, and 0.01. If and when you are in a situation where you have to decide what alpha level to use, you really need to think about the situation at hand and what is appropriate for that situation. And we're going to talk about a few issues in a minute that will help you that would help a person determine what an appropriate alpha level is. Now, the alpha level is usually called the significance level. When we reject the null hypothesis, we say that the test is significant at blah level, whatever alpha is. If our p-value does not fall below alpha, what we should say is the data have failed to provide sufficient evidence to reject the null hypothesis. You never, ever, ever say you accept the null hypothesis. You never, ever say that you prove either hypothesis. People are tempted to say those things because sometimes when you're trying to make sense of something, you want to rephrase it in your mind. Just be really careful. Recall that in a jury trial, if we do not find the defendant guilty, we say the defendant is not guilty. We don't say the defendant is innocent. The p-value gives the reader far more information than just stating that you reject or fail to reject the null. In fact, by providing a p-value to the reader, you allow that person to make his or her own decisions about the test. What you might consider statistically significant may not be the same as what someone else does. There could always be more than one alpha level that would have been chosen for a test, but because you have one set of data that you're using in this particular test, there is only one p-value. Okay, so when we say that a test is statistically significant, all we are saying is that a test statistic had a p-value lower than our alpha level. We're saying an effect was there, okay, that we do not think happened by chance alone. However, in order to know if the effect that we are seeing is large enough to be financially or scientifically significant, sociologically significant, you need a content expert to make that decision. That's why statistics is studied and required for so many different fields, because you need people who understand this testing process and then who understand, well, is the difference I'm seeing big enough to really make a practical difference? It is a good practice to report the magnitude of the difference between the observed statistic value and the null hypothesis value in the same units as the data, along with the p-value, so that people can get an idea of that difference and whether or not it is practically significant. Okay, confidence intervals and hypothesis tests are built from the same calculations, and we have the same assumptions and conditions, so you can approximate a hypothesis test by examining a confidence interval. Just ask whether the null hypothesis value is consistent with the confidence interval for the parameter at that corresponding confidence level. Basically, you're going to be looking to see if the null hypothesis value falls within the confidence interval. Because confidence intervals are two-sided, they correspond to two-sided tests. So in general, a confidence interval with a confidence level of C% corresponds to a two-sided hypothesis test with an alpha level of 100 minus C%. So 95% confidence level corresponds to a 5% significance level for a two-sided test. For one-sided tests, it's a little more complicated. You take that difference and divide it in half. So, for instance, back to our 95% confidence level, if then we are using that to test a one-sided claim, then you would have 1/2 of 5%, so 2.5% as your alpha level. Okay, so here's some shocking news for you. Nobody's perfect. Even with lots of evidence, we can still make the wrong decision. When we perform a test, when I say this, we've performed the hypothesis test perfectly. We followed every step of the way that we should, and we've checked every condition so that we can make the assumptions. Based on our best methods, we can still be wrong. And there's two ways we can be wrong. A type 1 error is that the null hypothesis is true, but we mistakenly reject it. And the type 2 error is the null hypothesis is false, but we fail to reject it. Which type of error is more serious depends on the situation at hand. In other words, the gravity of the error is context dependent. Here's an illustration of the 4 situations in a hypothesis test. Now, the truth is the truth. We may never know what the truth is, but it exists. And so either the null hypothesis is true or it's false. Now, based on our best methods and our data, we're either going to reject the null hypothesis or fail to reject. I guess for the sake of space, the people who made this put retain the null hypothesis. Remember, we don't really say that, and we fail to reject it. All right. So if we reject, we get a small p-value, we reject the null. We could either be absolutely where we want to be. We could be rejecting a false null, and that is perfect. This is what we're rooting for, and this is the power. The probability of this occurring is the power of the test, which we will talk about in a minute. If the null hypothesis is true, however, we have committed a type 1 error. Okay, we've made a mistake. And this is going to happen when our p-value is small enough for us to reject the null. So the probability of type 1 error is equal to alpha. Now, if we get a large p-value, we're not going to reject our null. And if the truth is that null is true, that's awesome. But So it's okay. The probability that this doesn't have a cool name for it or anything, or a cool symbol, because yeah, the test worked the way it should. It's consistent with truth, but we've kind of wasted our time. If the null hypothesis is really true, it's a little bit of a waste of time to go trying to collect evidence for an alternative against it and then conduct the test. So it's kind of, it's better than making a mistake, but it's still not really what we were rooting for. All right, the last scenario is that the null is false, but our p-value is large, so we don't reject it. This is a type 2 error, and we do have a symbol for that, and that is beta. Okay, so if the null is true, both of these two events right here have to have probabilities that add up to 1, because that's just one truth is that the null, that the null is true, and so the entire sample space of what can happen there is that we reject or don't reject the null. Over here, we have the null is false. And so remember I said the probability of this event is called power. The probability of a type 2 error is called beta, and those always add up to 1 because they represent 100% of the outcomes of our test if the null is false. And that's going to be important here in a minute. How often will a type 1 error occur? Since a type 1 error is rejecting a true null hypothesis, the probability of a type 1 error is our alpha level. When the null is false and we reject it, we have done the right thing. A test's ability to detect a false hypothesis is quantified by the power of the test, which is really what we're, that's a scenario that as a statistician or researcher, we are rooting for this. We are hoping we have data that will let us reject the null hypothesis and that it is actually a false hypothesis. When the null is false and we fail to reject it, we have made a type 2 error. We assign the letter beta to the probability of this mistake. It's harder to assess the value of beta because we don't know what the value of the parameter really is. There's no single value for beta. We can think of a whole collection of betas, one for each of the incorrect parameter value. If you really want to know about the calculation of power, it falls outside of the scope of this course to actually figure out or the probability of beta, probability of a type 2 error. But I am sure there are tons of videos and websites that explain it. We could reduce beta for all alternative parameter values by increasing alpha. So that's awesome. That would reduce beta, our probability of making a type 2 error, but it increases our probability of making a type 1 error. So there is this tension between type 1 and type 2 errors. The only way to reduce both types of errors is to collect more data. Otherwise, we just wind up trading off one kind of error against the other. Okay, so power is really important. The power of a test is the probability that it correctly rejects a false null hypothesis. When the power is high, we can be confident that we've looked hard enough at this situation. The power of a test is 1 minus beta, because beta is the probability that a test fails to reject a false null hypothesis, and that the power is the probability that it does reject the false null hypothesis. So the only way that you're going to need to know how to calculate beta is if somebody gives you power, and then you would need to be able to set that equal to 1 minus beta to solve for beta. Likewise, if someone gives you a value for beta, you need to do 1 minus that beta value to get the power. The value of the power depends on how far the truth lies from the null hypothesis value. The distance between the null hypothesis value P naught and the truth P, the actual population proportion, is called the effect size. Power depends directly on the effect size. The larger the effect size, the higher the power. So the further an observed value is from, or the hypothesis value is from the truth, that's going to increase the power. Obtaining a larger sample size decreases the probability of a type 2 error, so it increases the power. This is the only option we can control and reduce both types of errors. It also makes sense that the more we're willing to accept a type 1 error, the less likely we will be to make a type 2 error. Thus, as we increase alpha, we increase power. Okay. Soon after the euro was introduced as currency in Europe, it was widely reported that someone had spun the euro coin 250 times and gotten heads 140 times. We wished to test a hypothesis about the fairness of the spinning of the coin. So we want to estimate the true proportion of heads, and we're going to use a 95% confidence interval, and we are going to make sure we check the conditions. The first assumption we need to check conditions for is the independence assumption. Now, we're not doing random sampling here. The outcome of the spin of a coin is a random event. The statement here, though, that we can make is actually about the independence. Each result is independent of the last in the spinning of fair coins. So we can make that statement, and that directly goes to the independence assumption. We're not sampling from a population. There can be an infinite number of coin spins, so we don't need to check the 10% rule. It just doesn't apply here. We do need to check the success-failure rule just to make sure our sample size is large enough. A sample size our sample size is sufficiently large since there were 140 successes and 110 failures, both of which are greater than 10. If I wanted to make double sure I got credit for this, I would have put and 250 minus 140 equals 110 failures. All right. Then we put this information in our calculator and we get 0.498 to 0.62220. And we're going to, even if they don't ask you to interpret the confidence interval, especially if that's not in a follow-up question, go ahead and interpret it. We are 95% confident that the true proportion of heads is between 49.8% and 62.2%. Does your confidence interval provide evidence that the coin is unfair when spun? Explain. Okay, so when we are testing something like the fairness of a coin, it's going to be a two-sided test because it doesn't matter whether one of the proportions is above 0.5 or below 0.5, it's still unfair. So this would correspond to a 5% significance level, just in case you were curious. No, 50% is within the confidence interval, so it's a plausible value for the true proportion of heads. So we do not have significant evidence that the coin is unfair. What is the significance level of this test? Explain. Alpha equals 0.05, and it's a two-tailed test based on a 95% confidence interval. All right, let's look at another problem. Production managers on an assembly line must monitor the output to be sure that the level of defective products remains small. They periodically inspect a random sample of items produced. If they find a significant increase in the proportion of items that must be rejected, they will halt the assembly process until the problem can be identified and repaired. So in this context, what is a type 1 error? One thing that is often helpful to people is to write out what a type 1 error is and then put it in context. So type 1 error is rejecting a true null hypothesis. So let's think about what our null and alternative hypothesis would be. The null is that there is no change in the proportion of defective items. So we're saying the true proportion is equal to the usual true proportion. The alternative When we're going to stop the assembly process would be when the proportion is higher than usual. So if we reject the null hypothesis, it means that we're believing that there is an increase in the proportion of defective items when there has not been an increase. So a type 1 error would be deciding there has been an increase in defective items when there has not been one. Okay, everything's fine, but we think that there's a problem. So a type 2 error is failing to reject a false null hypothesis. So thinking about this again, we would fail to reject the null hypothesis. We would think that things are fine, but if it's false, then there really has been an increase in the number of defective items. So a type 2 error would be deciding there had been no increase in the number of defective products when there really had been an increase. Now remember, when we talk about these errors, they're not mistakes people have made in the process of doing their hypothesis test. They conducted their hypothesis test and came up with the correct conclusion based on the evidence. It's just that in reality, they are wrong. Okay, most of the time, you're not going to know if in a specific case you've made a type 1 or type 2 error. You just have to think about what they would be and then what the consequences would be and which one should be avoided as compared to the other one. So what type of error would the factory owner consider more serious? Well, the owner would probably consider a type 2 error more serious, depending on the cost of shutting the line down. Generally, because of warranty cost and lost customer loyalty, defects that are caught in the factory are much cheaper to fix than defects found after items are sold. Which type of error might customers consider more serious? The customers would actually probably be in agreement here and consider a type 2 error more serious. Nobody wants to get a defective product. So, unless it's just extremely expensive to shut down the line when it didn't need to, like in a type 1 error, it seems like in this situation, if they're trying to figure out, oh, when we set this test up, do we want to minimize type 1 or type 2 error? They would be in agreement with their customers that type 2 error should be the one that's minimized. Okay, so in this context, what is meant by the power of the test the inspectors conduct? That's the probability of correctly rejecting the null hypothesis. So it's the power would be the probability of deciding there has been an increase in the number of defectives when this is true. So they want to have a small beta value and a large power in this test. They are currently testing 5 items each hour. Someone has proposed they test 10 instead. So what are the advantages and disadvantages of such a change? So remember, by increasing your sample size, you can decrease both alpha and both probability of type 1 error, alpha, probability of type 2 error, beta, and at the same time, increase power. So lots of good advantages. There would be more power, but there would also be more work testing, and there could be more cost, and it could just make it really hard to produce enough items if you're doing that. The test currently uses a 5% level of significance. What are the advantages and disadvantages of changing to an alpha level of 1%? Well, the advantage would be that you have a smaller probability of a type 1 error. You reduce alpha, you reduce the probability of a type 1 error. The disadvantage is that you're going to have a greater probability of a type 2 error. And in this scenario, everybody probably thinks that type 2 error would be the worst of the case, worst of 2 bad situations. It's better to commit a type 1 error than a type 2 error. And anytime you increase type 2 error, you lower power. Suppose that as the day passes, one of the machines on the assembly line produces more and more items that are defective. How will this affect the power of the test? Well, as the day goes on, the power of the test is going to increase because the effect size difference between the expected number of defectives and the actual number of defectives is increasing. So it should be able to definitely pick up on a problem if it's getting worse and worse. All right, that's it. Go ahead and try the problems on your own. We will talk about this in class and go over those problems. Thank you so much for listening to the video, and I hope you have a great day.